Let me recap a little bit about the reflection. When you see the source of light like this from the lamp hitting this paper, what happening is that the atom, the electron inside the atom will be vibrate. Okay? And this vibration is not enough to excite the electron inside the atom of this paper to excite to the next energy level. So when that happens, it's either the vibration, this vibration either pass through or it got what we call reflected. Okay? Okay? Typically, it's got reflected lah. So in this case, there's energy, the all visible frequency from the white light hit this thing, and then the atom vibrate, the electron vibrate, and then what happen next is that this what we call, it will sort of like reflect back all the visible frequency to your eyes. That's why we see this thing black. For the black ink, it's basically the most of the what we call, most of the frequency from the white light is absorbed by the black ink. So that's why you see dark like that. So when you see something like red here, it means it absorbs everything except for example this red. So it's absorbed every wavelength, because remember the wavelength there are many. So we know the visible wavelength they are red, orange, yellow, green, and then what? Green, and then blue, indigo, and violet. So red normally is long like this. And then you have red, green, right, orange is basically is more shorter than that, and then you have red, orange, yellow, and shorter than that, and then you have what? Green. Where's my green? Green is even shorter, and so on lah. So let's say you have this red, green, red, orange. I don't have orange. Red, orange, yellow, and then green, and then so on lah. So basically, it's a mixture of the frequency coming to this what we call, to this let's say this lah, this red something lah, red something. So when you hit this thing, as I said, most of the thing is absorbed, most of the frequency is absorbed. What you get is basically just the red is reflected lah. That's why you see red. So this is your eyes. So when I said it's being absorbed, okay, what does it mean by it's being absorbed, this thing? When I said this thing is being absorbed, what does it mean? What does it mean? Okay, it means that, remember when we studied about resonance before, remember resonance? When we have Erica and Rifdi come in front and play with this slinky. So we talk about resonance, because now I want to what we call connect everything, resonance and also standing wave, standing wave. Okay, resonance simply basically the sudden increase in amplitude, amplitude. So meaning that if you have something like this and you give a resonance, this suddenly become twice bigger. So that's basically resonance. When we talk about standing wave, it's basically the term standing wave is what? Tanya, what is standing wave? You buat itu dalam exam, tak tahu lah nak reply macam mana. Okay, anyway, standing waves happen when typically you can find standing wave when you fix what we call the wave, when the wave have some fixed region lah. So for example like this, so you have like what we call the pole, the rope, you try to make a wave and then there are fixed region here, and then standing wave happen when you see the wave doesn't move. That's why it's standing still, doesn't move. Normally wave is move like this, right? Move like this. Okay, imagine this is moving. It's moving, right? It's moving. Standing wave is just like this and as if it's not moving. So because I'm writing, it's not like they are like simulation there, but basically you get the idea lah. Standing wave you see from the far is as if it's standing still. So the reason why is standing wave behave like that is because the standing wave occur because of two things. It's because of the resonance and also because of the interference. Okay. Okay. First we talk about the this resonance first. The resonance first. So we learned before that you can get the standing waves only when you give a certain frequency only. Cannot happen with any frequency. So that's why you need to give at certain frequency that match natural frequency of the material itself. That's basically where the resonance come into place for the standing wave, because you cannot get the standing wave if you just give the energy just like that. It need to be have at certain frequency that match the natural frequency. So when the given frequency match with the natural frequency, that's what we call resonance lah. For example, like this, you give another frequency that is matched with this. That's why it become bigger. So that's the idea lah. Okay, interference. How this interference have to do with the standing wave? If you look here, this thing, when you do, when the wave goes like this, right? Goes like this, and then when the wave reach here, it will reflect. Somehow it will reflect, and then difficult lah. And then and then this will give thing. Okay, so this will go here, this will go here. Meaning that if you try to make a wave from here, so let's say we call it wave number 1. Wave number 1 we go to the pole, near the pole, and then reflected back, and then another wave coming in. So when this wave, what we call, apa orang kata, meet each other, it will create this thing lah, the interference, the destructive interference, meaning that this thing, you have this thing and this thing meet each other, so it will become zero lah. So that's why in standing wave you will see something like this. You see, if you put something in the middle like that, you see this thing as if like doesn't move. I mean, there are node and antinode here. This antinode. The reason why this happened, meaning that why they are frozen still, is because of interference occur at the same time. Okay, resonance and interference occur at the same time. Okay, so when this thing absorb, when this other frequency is absorbed by this red molecule, what does it mean is that this all frequency carries with it is energy, because we know that energy is basically frequency and lambda. So that is energy. Yeah, ke? No. Frequency with the Planck constant. Planck constant plus lambda like this. Okay. So we learned this before. The energy that is carried by each frequency equal to a Planck constant plus the lambda. Okay. If you forget about this, please read before lah. Okay. So meaning that it carries some energy. So this energy sort of like absorbed by this. What does it mean by being absorbed? Meaning that this energy match with the natural frequency of the whatever this material, this red material. So this red material, inside this red material, okay. So this thing, the orange, yellow, green, and then blue, indigo, and violet, hit this thing, and then it's being absorbed. When it's being absorbed, meaning that the frequency for this match with the frequency of this material, this pigment. So it's being absorbed. That's why it cannot be reflected. So being absorbed meaning that it will sort of like excited to the net energy level lah. So it's not really stable on the top, and then it goes down. But then in this case, when I said that this thing, so you have the electron excited to next energy level, and then it goes down. Normally I show that they are like something coming out, right? This something coming out can be in terms of visible light, but it also can be like heat, radiation, or whatever. So not necessarily when something goes down, you see something. Okay, it is depend on the energy level, because in order for the electron move to the top, it need to have to gain the energy in such a way that it's exactly same with this difference lah. The energy level for this different. We learned before also why they are orbit in the electron and so on, because we talk about the electron have the what we call the standing wave also, and then we have this whatever, something like that. We have covered this before under this de Broglie wavelength lah, wavelength, to show that every electron can behave like a wave. Okay, can behave like a wave. You refer back this part lah if you don't unclear about this thing. Okay, so that's the thing lah. So you see that thing is red because other frequency then red is being absorbed, and that frequency is matched the resonance for that pigment inside the what we call inside the chair, so that it will what we call, it will being absorbed lah. So now if that the case, why glass is transparent? Why glass transparent? Why this glass is transparent? What happened when you shine something, this thing go to glass? Let's say you have glass here. Why glass is transparent? You have the light. Why glass is transparent at all? Huh? Sorry? But why? Why light go through? Huh? Okay. The glass, yeah, it's true lah, light go through. But the reason why, because you need to remember, the light is made up, the visible light here, made up with this spectrum of energy. There are many. I mean, this, like for example, typically red, the wavelength for the red is around like, I think 800 nanometer. And for the blue light at the bottom, they are blue light. They are blue light here. At the bottom, they are blue light, which is much more energetic. So the wavelength for this is around 400 lah, 400 nanometer. So visible light is between 400 nanometer to 800 nanometer in terms of wavelength lah. That's the visible light. So this visible light, as I said before, is carried with energy. So when it goes to, it hit the glass surface, so what happen actually is still this thing, because it's energy. The light is still energy, meaning that you give energy to the glass, but this energy is not enough to sort of being absorbed, or also being what we call being absorbed, meaning that it match the frequency lah, like this being absorbed, or so it just go pass through lah. Okay, so in other word, when what we call the resonant frequency, okay, when, for example, when the material and the what we call the energy that is hit the material itself have what we call can produce a resonance, then that material will absorb the light lah. For example, like the opaque material, the reason why it's opaque is because this energy that is hitting that material is what we call at the resonance with the vibration, the natural vibration for the material itself. So that's why the reason you see the opaque. But for the glass, all the visible length frequency unable to resonate the material, the electron inside the atom of the glass. Okay, so all the visible frequency unable to resonate the electron in glass atom lah. Glass atom. That's what does it mean lah. That's why you go pass through. Okay. But if you try to shine the UV, if let's say this is UV, let's say this is UV. Okay. This is light. This is the light. This is visible light. Okay. The visible light just go pass through. Okay. That is the visible light. But for UV, it will be absorbed. It will be absorbed by the glass itself. Meaning that the UV have the same resonance with the glass itself. So UV will not pass through through the glass lah. So if you have glass here, and then you have UV, it will absorb. But if you have like a visible light like this you just pass through. So visible light, this is UV. Okay. So the reason because the UV is capable to what we call to being absorbed by the glass itself lah. Okay. Okay, that's the reason. Okay, this thing might be, that's why you don't get this what we call suntan in the car. You don't get like sunburn in the car or in the house, even though you have like transparent glass, you don't get sunburn. Because what causes the sunburn is the UV itself. The sun, you have sun here. Normally they have a UVA, UVB, UVA, and a UVB, and a UVC. Okay, UVC is the most dangerous lah. So when the sun hit the earth, the UVC is basically is being absorbed or being reflected lah. What coming down is basically UVA and also UVB lah, UVE. UVA is what make you tan or sunburn lah, because it's UV. So this UVA, if you are in the car, and you have this what we call the glass, so the glass is basically protect you from the UVA. You still get the visible light because the sun, apart from the UV, they also give you the visible light also, visible light. So the visible light just go through to your car, but then the UV will be what we call being absorbed by the glass itself. When you have something like what we call this thing, UV lamp like that, and then I have, you see before, something like this. What you see here, this is not UV. This is UV lah, but UVA. This UVA is not dangerous, but prolong is not. I mean, it's not really dangerous lah. The UV that is used for counterfeit is not really dangerous because this is UVA, not UVC. The one in the lab is UVC. The one that kill the bacteria is UVC. So if I have this thing, UVA, and then I have what we call the glass here, do you think it will pass through or not? Do you think it will pass through or not? Okay. Let's say I have cuvette here. So I have this thing, and then this thing is still pass through. You see, they still pass through. I mean, it's not clear here. Umi, macam biasa. Can you help me with this thing? I think put here lah, easy. So Umi will be, this is your job. Okay. So basically, let's say I said that the UV, the glass will absorb the UV. Why then? Where is the camera? The camera is there. Okay, over there. So let's say this you can see front. Okay, so that is, so if I put this thing, mana? So you can see they are what we call, they are fluorescent light, right? Okay, so they are fluorescent light. So now this is a cuvette. This is made from plastic, not glass. But plastic also can absorb UV. Meaning that plastic, if you change this, what we call the windscreen for the car with the plastic also is okay because it also absorbs. But if I put here, still you can see right, it just go past. Oh, dia tak nampak. Nampak tak? Okay, so it passed through, right? Okay, but if I have this, sorry. Okay, here there are another cuvette. This is quartz cuvette. Quartz is different than plastic. Okay, normally people use quartz cuvette for what we call to measure something that is absorb UV, because this will absorb UV. Meaning that if let's say you want to test, for example, you know that pegang saya. Duduk je situ. So for example, you know that cuvette, you have learned the cuvette before. Sometimes you irradiate this cuvette with, for example, when you want to see the OD for bacteria, you use 560 nanometer, right? Something like that lah. You have done this in the lab 1. Okay, meaning that you put something in the cuvette and then you put in the spectrophotometer and then you shine this whatever nanometer. So 560 nanometer meaning that it is in green, meaning that you shine the green laser actually, green color. But the UV spectrophotometer, UV spectrophotometer, okay, the one that is in the lab, have the range between 180, I think, until 1200 nanometer, meaning that you can create, you can give the wavelength, specific wavelength. Which wavelength do you want? For example, between 180 nanometer to 1200 nanometer. As I said before, between 400 and 800 is basically the visible region. Okay, so meaning that if let's say you shine 560 nanometer, meaning that you are shining sort of like green light to this lah, to the cuvette. You don't see because you close it, right? But if you can see, it's a green light. So now, this, whatever below this is a UV region. UV region, meaning that, as I said before, plastic can sort of like absorb the UV region. By right, if you use the normal plastic here, you put here, and then you try to shine, for example, 200 nanometer, this plastic will absorb that thing. This plastic will absorb the, will absorb the frequency lah, and then it cannot pass through. By right, it will do that. But if you look here, if I like siapa nama you? Umi Okay, it seems like nothing happened, right? Meaning that the plastic doesn't doesn't absorb the UV, because you need to understand the UV. Even though we said UV is below the visible light, but it's a spectrum. Meaning that when I say spectrum, okay, you can see, but later I call you back. When I say spectrum, what is the thing? When I say spectrum, this thing. Okay. When I say spectrum, there are no sharp edge. You don't see where it starts, where it ends. It's just a mixture. So you see here UV. They are short wavelength UV, and they also long range UV. This is what we call near visible light UV lah. This is where the UVA, which is less dangerous, and then this is UVB, this is UVC. The one that kills the bacteria is UVC. The one that used for what we call fluorescent in the banknote or whatever, the counterfeit banknote, they use UVA. So the UVA, as you can see, is not being absorbed by the glass or plastic. But if I have a real UV, Umi, come. Mana saya punya penutup? Umi, you ambil penutup. Penutup saya mana? Oh, okay. So here is I borrow the UV from buka tu. Buka. Erika buka. Tak apa. Boleh buka? Tak apa, buka. So this is basically UVC. Okay. So if you look here, so here inside on the what we call UV lamp, the proper UV lamp, they have long wave and short wave. Long wave meaning that it's not energetic enough. Okay. It's not energetic enough. Tak apa, you can. Yeah. Okay. Where is the thing? Okay. Okay. So this UV lamp, if you look here, they are what we call, they are basically the short wave. Nampak? They are short wave and also long wave. So the short wave is more energetic lah. So the short wave is more energetic one, and then the long wave is less energetic. The long wave here is equivalent to this lah. We call it black light. So it's a UVA. This short wave is UVC. The one that in your, what we call, in your lamina hood lah, lamina hood. So if I go for long wave, this I put long wave. So if I go here, so you can see they are still near, dekat sikit. You can see it pass through. Focus sikit. Bawa macam focus, pandai lagi focus. Okay, you can see it pass through, right? But if I change to this is UVC. So they are not pass through. I mean, difficult to see lah. I mean, let me put this thing. So you have quartz here and this thing. Okay, so let me. Okay, can you put there? Kalau kau tutup ni. Okay, so you can see there. You cannot see. Macam mana ni? let me put here. Okay. You see or not? So there are one, depan sikit, ni depan sikit. Okay, there are one cuvette that is, for example, is as if it's absorbed, right? So the one here, this one is basically plastic lah. So it's absorbed UV. That's why if I shine the UV, this is UVC, that's why it's absorbed. Okay, this one is quartz, the one that is passed through. I mean that when the UV light, what you call pass through, mean that it allow the UV light go. So this is quartz. So if you want to try to sort of like measure something that is have the site at the what we call short UV length, then you need to use quartz lah, because this doesn't absorb what we call absorb the UV, but the normal plastic cuvette will absorb the UV. Okay, so that's it. Thank you. So that's why when you are trying to what we call trying to use the cuvette, even the simple thing like a cuvette have something to do with the wave. Okay, if you just take the cuvette, your supervisor asks you go to the lab and find the OD for something, and then you just go there, plug into the spectrophotometer without thinking, you get the result. You will get the result if you use the wrong cuvette. You still get the result. The machine will give you the numbers, but the numbers is wrong lah. So that's why it's important for you to understand the basic, the fundamental, at least understand the fundamental about the wave, because wave, if, as you can see, even the UV spectrophotometer, the one that you use normally, also based on the wave. The FTIR also based on the wave. The SRD based on the wave. The electron microscope based on the wave. The normal microscope also, light is also the wave. So most of the analytical tool that you can find in the lab is basically based on the wave. That's why understanding the wave can help you more on ni lah, understanding what you do lah. Okay, so let me close this thing. Okay, this is where this thing. So let me put here. Okay, so now that's about, this is basically about the absorption lah, absorption and transmission. So now I want to ask something about here. So now we talk about glass. We talk about glass thing. We know that UV cannot penetrate the glass, the UVC lah, the dangerous UV cannot penetrate, the UVB cannot penetrate the glass. Okay, because of the absorption. Okay, the light can travel pass through, but you know that the light when travel pass through the glass, it will not, somehow it will bend, right? Somehow it will bend. Why it bend? Because we know it passed through, but it bend. Why then it bend? Let me. Why it bend? Why when light pass through the glass it bend? What? Yalah, refraction is refraction, but why? Why it's bend at the first place? Why light refract? Why light bend? Refraction is the phenomena, light bend, but then why it bend at the first place? Huh? Different medium? Yeah, but why? I have this glass, this air, and then let me put a straight line first. Let's say this A and this B. Let me draw a straight line. So this is the shortest path to A and B. Okay, but when you shine the light, what happens is that it goes here, and then it goes here, it goes here, something like that lah. Something like that. They bend here. Okay, this not. I don't know lah how to draw. How to draw? Difficult to draw. Because it's difficult to draw here. So this will be. So this B, and then this light, normally they bend something like this, okay, and then something like this. Okay, so like that lah, roughly the idea. Meaning that the light bend here, it not goes to the straight line. The reason for this is because the light will travel at different speed here. Light travel travel at different speed here. Okay, so the idea is the reason why the light travel at different speed at the first place is because the light will try to reach B, for example, the A to B, the light try to reach B at the least possible time. Light, or any wave lah, try to travel at least time possible. So least time possible doesn't necessarily mean the straight line. The analogy is like this. Let's say we have Safwan here, Safwan Fatih here on the shore. This beach. Safwan work as a lifeguard. On the beach, and then suddenly Safwan saw Iman struggling here. Had like that. Okay, so this is Iman. So this is C. This is C. So this is C. That's beach. Okay. So let's say Safwan position is at A, and then Iman position is at B. Okay, position Iman as B. What is the quickest path for Safwan to save Iman? Straight line? It's not necessarily straight line, because if you look here, Safwan can go straight like this. 1, 2. Let's say I go like this, straight like this. But when Safwan did like this, let me draw carefully lah. Let me draw like this. So B is here. Let me put pond. Okay, so this is what happened when Safwan tried to save Iman by running straight to the Iman on the straight path. What happened here, if you look here, where is my green? Safwan or use, for example, this time in water. We as human can run faster on sand than in water, right? Human can run faster than swim, right? So this is what happened when Safwan tried to save Iman on the straight line. But the more more efficient way to save Iman is basically to go this way. Because Safwan can run fast on the beach, and then he tried to minimize the amount in water. So if you look here, so this is basically the amount time in water. So by efficiency, this blue path is more efficient than this black path, the dash path here. Even though this dash path is the shortest one, but the shortest one here doesn't necessarily mean the fastest. Understand? The shortest not necessarily mean the fastest in this case, because you are traveling at two different medium. That's why if you are in the same medium, straight line is the fastest lah. But if you have two different medium like this like the sand, this like water, it will the bending, this path is much more quick lah, This what happened to the light or sound, whatever lah. But especially for the light. That's why light bend here, because light try to minimize the amount inside the glass. If you look here, the blue, you see, is longer than here lah. The hypotenuse is longer than the red one. So that's why light bend. So this is what we call the refraction. This refraction. The bending of light, bending of wave or light, bending of wave or light when wave lah, generic, because sound also can be refracted. Bending of wave when it travel across different medium. medium. Okay, when refraction happen, what occur is that the speed also change. The speed also change because as you see here, swimming is slower than running. So that also, if we put that analogy here, we also said that the light travel at different speed, in a medium. So this travel at, I say light because to make things easier, the light travel at different speed in a different medium. For example, the air, the index of refraction, this is what we call the index of refraction. Index, how much slower the light travel, index of refraction in vacuum is 1. Okay, in air is 1.000, I don't remember, but 2 something lah. And then in glass, in water, is basically 1.33. In glass is 1.52 like that. In diamond is basically 2.42. What does it mean? Index of refraction is basically the speed of light. So index of refraction basically the speed of light in vacuum over speed of light in medium lah, So that's basically index of refraction meaning that if, for example, let's say water 1.33, meaning that we know the speed of light is what? Let's say we put C, speed of light is C, and then we put water 1.33 equal to speed of light in vacuum, let's say C, over speed of light in the medium here. So this, understand tak? Faham tak ni? This is like one equation here. Okay, now we look at the water. Water is 1.3. So speed of light in vacuum, let's say we put C lah. And then I don't know what is, we want to know what is this question mark. So the question mark here is basically what? C over ni kan? C over 1.33. How much is this? 1 over 1.33. Let's say 1, C, let's put 1. C, imagine C is 1 lah, 1 over 133. How much? 0.75, right? Something, 0.75 C lah. Meaning that in the water, the light travel 75% the speed of the light, the actual light. So that's what does it mean lah. So it's slower lah. So goes to glass is much more slower and slower. So this is what we call index of refraction, the ratio between speed light in vacuum over speed of light in the medium. And for this thing, you see, so we know this is slower, but also we can see also there are angle, right? There are different angle. So in the what we call in the refraction field, not field lah, I mean in under refraction, I think you know something about the Snell law. Snell law allow you to know what is the angle of incident and what is angle here. Okay, for example, the Snell law said that n1 sin theta 1 equal to n2 sin theta 2. Okay, what does it mean? This you have learned in the high school, I think. So let's say you have something like this, and then this is water. Let's say this water, this air. Okay, when the light come through like this, okay, you know the water will bend. Okay, so imagine we make sort of like the normal plane here. So this we draw the normal plane. So this is what we call normal plane. Okay, so this theta 1 is basically the angle between this and this, between this normal and the incident light. So imagine the light coming through the water like this. Okay, so this is theta 1. That's what does it mean. So we know that when it goes to water, it will bend. So it will bend somehow like this. Okay, somehow like that. It bend like that. So this is what we call theta 2. So using this law, you can get the amount how much is bent. let's say this theta 1 is 45 degree. Let's say you shine the light at 45 degree. What is the bend for this? What is the amount of the bending here? Anyone? Okay. What is the bend here? What is the bend there? So you have N1. N1 for air is 1. For water is 1.33, right? So basically you put 1 and then sine 45 and then equal to N2. N2 is 133, 1.33, and then you don't know theta 2. So theta 2 is basically sine 45 degree over 1.33. Berapa? So theta 2 is basically berapa? So basically you calculate all this thing, you get 32 degrees. So you know this is basically, you become 32 degree. So under the refraction, you know that this travels slow, and also you can measure what we call the angle, the bending angle, the bending angle of this thing. Okay. So this phenomena, the refraction, is what caused the rainbow to happen lah. Because when you have a rainbow, it's basically refraction and reflection together lah. For example, let's say this is drop of water, and then if let's say the sunlight coming in, let's say the sunlight coming in. Remember, the sunlight is made up from the the spectrum of the visible light, red until the blue. So it turned out that red is faster than the purple lah, The red here is faster than this purple in the medium. All these things travel at equal speed in vacuum, speed of light. But when it goes to the medium, it's change the speed. You see, you see, it's change the speed, right? It's change the speed. So in a medium, in medium, the red is faster than in the blue. So you will see when, let's say this is the, what we call, this is the light. Light is, let's say this light coming from here. So what will happen is that the red will be sort of like diffracted, will sort of like bended. Because in water, right, this water, this air, water droplet, okay? And then the blue also will be refracted, okay? So like that. So this thing, and then something like this, okay? So this, when the sunlight goes to the raindrop, what happens is refraction happen. And because the red will be reflected less than the blue, so this what will happen, it will be separate. So this separation, we call it dispersion. And this, when it reaches to the side of the, what we call, on the drop, it will reflect to here. It will reflect. This also will reflect lah. Will reflect. There are some that will be diffract. They will diffract also here. They also will diffract here also. They will also diffract. Okay. But some will be reflected, and here it will further, what we call, diffract here. It further diffract. Okay. So this, what we call diffraction. Not diffraction. Refraction. Okay. This also what we call refraction. So, but remember this also, sorry to say, this thing, when it reaches here, it also can reflect. This also can reflect. Okay. They can also reflect. So the one that I put in black here, this one, and this one, this is reflection. It's reflect. So when rainbow happens, it's basically the function of reflection and refraction. Because when the light goes through any medium, it can be refract and also reflect. Okay, it can refract and also it can reflect. So this thing, because you have double refraction here This refraction number 1, this is refraction number 2. This angle become more pronounced. That's why you can see the rainbow lah. You can see the rainbow. You can see the separation of the color because of this double refraction. Let me show you the simulation lah, much easier. I go for this pad, refraction, reflect. I don't know. Bending light. So much easier if I show here lah. But the idea, this cause separation lah. This cause separation. This is separation of light. Separation of light is called dispersion lah. Dispersion. Let me go there. Okay. So let me grow this here. Okay, pad. So let me close this. It's easier. Fine. Takes time, That's low here. Okay, so you see here. Okay, so for example, let's say I put the ray, I click here. So you can see there are certain things that is diffracted. There are some light reflected. So it's happened together. So you can take this, put this, whatever this thing, put here. You can see 5.29% intensity lah. But if you go here, 94. But if you go like this, you bring here, it change lah. It change, the intensity change and so on. But to show that when you try to shine a light or wave to any medium, it can be refracted and it can be reflected together like that. If you try to show in the waveform, so you can get also like this. Alamak, ini kecil lah. Boleh nampak? It's same like this lah. So when you go, apa ni? Salah ni. Okay. Oh my! So you can see the amount of light and so on lah. Ada. Okay, 60 minutes. Okay, so that is the thing. So you can see also if you put this, you can play around lah in the what happen when you try to put in glass. So it will, you see, for example, the angle will be more pronounced when you try to put in the glass and so on. So that is basically the thing. So if you look at the prism here, for example, if I put prism here and I show the light, so you can see that there are refraction and also reflection. So I click here, so you see there are also reflection. So that's happened inside this thing lah. There are reflection and also refraction happen at the same time. But normally for the make thing easy, normally in the book they just show one pass only. When they talk about refraction, they just show refraction. But in reality, this is what happened. There are mixture of a lot of things, refraction, reflection, and so on. So that's why you can see. So this thing. So at certain angle, so for example, there are some magic angle that you can get this total. Okay, so you can see that there are certain magic angle. There are no, if you try to make in such a way that there are no reflection and no, what we call 100% reflected. This is what we call reflected. This is not refraction. Refraction, this thing. Refraction, this is refraction. Okay, this is reflection. This is reflection. Reflection, refraction. So you need to be clear about that. So there are certain angle that you can get what we call perfect reflection. This is what we call total internal reflection. Let me put here. When you have what we call, when you shine something to the glass or whatever, different medium light. when it goes here and then it sort of like totally reflected, meaning that there are no diffraction happen here. Usually there are diffraction happen even though it's a very low intensity, but if it totally reflected, what does it mean? This is what we call total reflection. Reflection. When there are no diffraction, when all the incident light is reflected by the medium. It's only happen at a certain angle. This is what we call the principle behind all the fiber optic, and also if you ever use this FTIR, some of you have used this thing. They use this total internal reflection. That's why they call ATR, total reflection, FTIR. So basically, you have like a diamond in the machine. You put a sample here, and then you shine the IR at the bottom, and then it will reflect here. So this is basically the what we call the basis of FTIR, the ATR FTIR, attenuated total reflection of infrared. Inilah. So basically that's what happened lah. What happened when you try to what we call just to show that the refraction and reflection normally occur at the same time. Okay, so that's the idea lah behind this thing. Okay, this also happened to the what we call to sound. Okay, to sound. I think diffraction. I think later lah. Tak habis juga. Okay, this also occur for the sound. So this is the light. The light you can see. But how about the sound? How about the sound? The sound also is a wave. So it can also being refracted. Okay. Sometimes you, let's say here, let's say this is like what we call, for the sound, light travel faster, sound travel faster in warm air than cool air. So that is the idea for the sound lah. So in the medium for the sound, it's like this. Okay, for the light, you know, this like glass, whatever. But for sound, it's like this. Sound travel faster in warm air than the cool air. So for example, this is Tanya here, and this is what we call siapa? Afiq here. Afiq. Okay. Sometimes this, let's say this is the leg, Okay, the leg in the middle. Okay. So sometimes there are times that when you can hear, for example, Tanya try to shout to Afiq. Sometimes Afiq can hear it very clearly. Sometimes it's not. There are reasons for that. For example, in the morning, in the afternoon, when Tanya shout, let's say shout very loud. Where is my green? Very loud so the sound wave something like this, right? This sound wave, right? So it goes like that. Okay. Tanya try to what we call to shout to Afiq like that. But in the noon, Afiq just cannot really hear very visibly lah. The reason because of that, you see this is the sound wave generated, and in the afternoon, let's say all these things at the same temperature, and remember the wave, the one of the properties of the wave is that the propagation of the wave, the wave front, it will move like this, perpendicular to the wave itself lah. I mean that the direction of the wave. We learned about the transverse and also the longitudinal wave before. So it's have something to do with the direction of the wave. And the direction of the wave is always perpendicular to the wave front itself. This is what we call wave front lah. This one, we call it wave front. Wave front. This is what we call direction of the wave. Direction of the direction of the wave. Okay. So can you see? Direction of the wave. Direction of the wave. Okay. So in the morning or in the afternoon, this is what happen lah. The temperature up and bottom is more or less the same lah. So the wave front goes like that, that, and the wavefront goes like that, something like this. So this is perpendicular, 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 and so on lah. So that's the reason why the Afiq cannot really hear very very clearly lah what Tanya shout because of this. But at the night time, remember the water have high heat capacity. You learn in the chemistry, water is one of the liquid that have high heat capacity. What does it mean is that it can retain the heat. In the noon, it will retain the heat at night. So that's why you found that at night the water is not as cold as you want. I mean, because it's retained the heat from the afternoon, whatever. So what happened now, this now become the heat air, the hot air, the warm air here, and not warm air, cool lah. No, this not. Okay, so this is the thing. So at night, at the early night, the water still hot. Mean the water still what we call still retain the heat from the afternoon. So meaning that the temperature here and the temperature here is more or less the same. But at the midnight, after a long time ago, the water become cool, become a little bit colder than before lah, because the heat is released. So now you found that this thing above this water is a cold air, and then the up here is still the warm air lah, warm air. So as I said that here, the sound travel faster in warm air. What does it mean? That is that instead of now, so instead of here, so the sound will be somehow here in the warm air, somehow here, faster. But in the cold air, is basically become like what we call shorter, right? Shorter and shorter here. So now if you try to draw, it becomes something like this. Something like this, and then something like this, something like this lah, something like that. Okay, so now the what we call the wavefront will be some sort of like bend. Let me put in the red color. Somehow it become bend because it's perpendicular. It's more like bended lah, instead of because this is perpendicular, 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 perpendicular. That's why at night, this what we call the sound from Tanya is much clearer than at the morning. So this is basically the refraction of the sound wave. Okay, the sound travels slower in the warm air, in the cold air than in a warm air. So refraction can occur both in the what we call for the light and also for the sound wave. Okay. So that is basically the idea of the refraction lah. Refraction is a bending of the sound because of its travel to across a different what we call different medium, different region. In this case, in the case of the light, is either glass or whatever medium. In case of the sound, is about the temperature gradient. Temperature gradient. That's why for what we call for the submarine under the sea, this submarine diffraction is a good thing for the submarine, because normally when people want to detect where is the submarine, they will use sonar, the what we call the sound wave. But we know that in the sea there are temperature gradient. There are temperature gradient here in the sea. Temperature gradient. So the temperature on the top is different than the bottom. So what will happen, even though for example, let's say the enemy try to use sonar to detect where is the submarine, because of temperature gradient, the sonar will be bended. So that's why. So whatever they got is not necessarily the correct location lah. So this refraction is a good thing for this submarine lah, because it can sort of like hide from this sonar. Okay, so that is basically refraction.